This is Kevin Cole at the University of Nebraska. The topic is heat transfer and the example is brick wall heated by sunshine. A west-facing brick wall, initially at uniform temperature 0°C, is heated by the afternoon sun. I have such a house, such a wall in my house, and inside is a bedroom. And in that bedroom, it takes a while in the springtime for a warm day to penetrate the house. So I constructed this example. We're going to model the wall as a homogeneous body, and we're going to assume that there's a constant heat flux at the surface rather than the sunshine. So part A, we're going to look for the heat flux value representative of afternoon sunshine. We're going to look for the heating time needed for the back wall, the inside wall, to warm up by 20°C, and we're going to look for the temperature on the heated side of the wall at that time. That's part C. So let's look at part A. If we look up the solar constant, it's 1,367 watts per meter squared. That's outside the atmosphere. So we need to adjust that. And let's say that this is reduced to 75% of that by the atmosphere. We've got the properties of the brick. That's the absorptivity, 0.94. And we've got some geometry here. If the sun were right overhead, that would be noon here. If the sun were down here, this would be 6 p.m. Let's say that the sun is somewhere in the afternoon, call that 3 p.m. And somewhere around that time is where we're going to assume that we've got the sun shining. So we need an angle adjustment, 45 degrees, to get the component perpendicular to the wall. So let's take our solar constant 1367 watts per meter squared, and we'll adjust it by the atmosphere, 0.75. We'll adjust it by the brick absorption, 0.94. We'll adjust it by the angle, sine of 45 degrees. If you do that, we're reduced to 681 watts per meter squared. All right, that's our heat flux. Part B, we're going to work with this model, and we're going to take some data from an existing solution published on the internet at exact.unl.edu, and it's organized by this number here. That number means heating at the surface, insulated at the back, and initial temperature uniform. Let's find that solution. Takes a moment for my computer here. All right, so here's the problem, the geometry we're talking about. And if I want to scroll down a bit and look at the geometry, it's heated on this side and it's insulated on that side, and it's initially uniform temperature. Let's ponder. We'll scroll down here. It's got some formulas and so on. We're going to get results. Here it is. We're going to get results in terms of a dimensionless temperature and a dimensionless time. So we're going to use these relationships. Let's start out with the dimensionless temperature. So the dimensionless temperature has the form T tilde, equals T minus T initial divided by Q naught L over K. Let's look at this grouping. Q naught L over K, we're going to need that. Our Q naught is 681. Our length is, that's in watts per meter squared. Our length is thickness of the brick, 3.5 inches. I'm going to convert that to meters by 0.0254 meters per inch. And then my conductivity here of the brick is 0.72 watts per meter per Kelvin. Let me do one thing. this, I'm going to use this length again later. This length here is 0.0889 meters. We're going to use that later. In this conversion, the inches go out, the watts go out, and meters squared, all that's left is Kelvin. So this unit, this quantity, when I compute it, is comes out to be 84.1 degrees Kelvin. All right, now let me go back to this definition here of my dimensionless temperature and compute that. T tilde is going to be the temperature rise, the temperature, final temperature measured is 20 C, initial temperature is 0, and this grouping is 84.1 Kelvin, so that this quantity, this ratio is 0.238. So that is the value of the dimensionless temperature I want to define the endpoint. Let's go back to the temperature solution. Come on, there it's loaded. All right. We're working with this dimensionless temperature here. If we scroll through this document, there's formulas and descriptions, but there's also some plots. Here's what I want. Here is a plot of the dimensionless temperature versus dimensionless time. And it's for a couple locations. The surface location, the temperature immediately rises right from 0 and it continues up. In contrast, the temperature at x over L equals 1 has a delay period right here. The temperature is flat and then it goes up. And that's the behavior that we're seeing in the brick wall that we want to understand. All right, continue looking deeper in this document. There's a table of numeric values. And what's here are dimensionless temperature in this table, and listed as a function of dimensionless time at the surface and at the back. So we're not interested in the front, we're interested in the back. So when the back temperature reaches the value we calculated, 0.238, and this is close, we could interpolate, but I'm going to go ahead and just take the value off the table. 0.238 is close to this value, 0.237. The dimensionless time is 0.4. So that's the result that we want for at this point in the problem. Let me go back to the problem statement. We want to say that at this time, at this temperature, this occurs at dimensionless time 0.4, and this is from table 1 in the solution. The solution was X22B10T0. All right, now we're going to have to find out what that time is in seconds by using the definition of dimensionless time. It was alpha t on L squared from that other document. What's alpha? Well, alpha is defined to be K on rho Cp. That's the thermal diffusivity. And we have some values of the properties. We have the conductivity, we have the density, and we have the specific heat. So I'm going to use those values. I'm not sure I can fit them on the same page here. Conductivity is 0.72 watts per meter per Kelvin. Density is 1900 kilograms per meters cubed. Specific heat is 835 joules per kilogram per Kelvin. Let's look at the units for a moment. The kelvins go out, kilograms go out, meters and meters cubed combined to be meters squared, and let's see, units I'll say. We get a meter squared, and then a watt divided by a joule. A watt is a joule per second, so we end up with meters squared per second. And the numbers turn out to be 0.72 divided by 1900 divided by 835. The numbers turn out to be 4.54 times 10 to the minus 7th. And again, the units are meters squared per second. So that's the thermal diffusivity. All right, and that's using the definition of dimensionless time. We need to unpack this and solve for the time in seconds. It's going to be dimensionless time, T tilde, times L squared over alpha. So the dimensionless time was 0.4. The length from up here was 0.0889 meters, that's the thickness of the wall, squared, and we're dividing by the thermal diffusivity, which we just found, 4.54 times 10 to the minus 7 meters squared per second. Meters squared goes out, seconds comes upstairs, and this is 63 seconds. That's also 1.93 hour. So that's the delay time. So it takes quite a while for the heat to penetrate the brick wall of my house on a sunny afternoon. All right, that takes care of part B. Part C asks, what's the temperature at the x equals 0 phase at this time? And we can get that information by going back to the table, if it will load here. There we are. Rather than the x equals 1 phase now, I'm interested in the x equals 0 phase. And we're talking about this dimensionless time here, and that dimensionless temperature is about 0.729. So that's the temperature dimensionless form at the front face. So the answer is from the table. It gives the dimensionless temperature is 0.729, at dimensionless time 0.4. What is the temperature in centigrade at that location? That isn't very helpful. We need to convert that. Well, the dimensionless temperature definition is up here. So we're going to unpack that and recast it in terms of T in units. So let me solve that. T of the units is going to be T initial plus T tilde times this grouping Q naught L over K. And now we can put some numbers in for that. Our initial temperature is 0C. T tilde is 0.729. That's the dimensionless temperature at this condition. And this grouping here we found earlier was 84.1 kelvins. And when I multiply that, I get 61.3 C. Now you might say, wait a minute, how can I combine degrees Kelvin, centigrade and degrees Kelvin in one equation? Well, it turns out that a temperature change of 1 degree Kelvin is the same as a temperature change of 1 degree centigrade, because the difference between centigrade and Kelvin is just the reference point, the point where you describe it to be 0. Okay, so that's our temperature in centigrade. We could convert that to Fahrenheit if we wanted, and that would be 61.3 C. We need to multiply by the conversion for the size of the degrees. There's 1.8 degree Fahrenheit in each degree centigrade, and then we have to add 32 because that's the ice point. And this value is 142 Fahrenheit. That's too hot to touch. So brick walls warm up. All right, we solved the problem. Let's recap. We were talking about a west-facing brick wall heated by the sun. We want to know how rapidly the back of the wall, approximated by this insulated condition, warms up. We approximated the solar constant as a heat flux, and we adjusted it by some atmospheric effects and absorption effects and angle effect to find the value there. We used an existing model, a solution we got from exact.unl.edu, located under this number, describing the geometry. We used dimensionless temperature and dimensionless time from table values to unpack the results to get a time in seconds when we converted. When we rearranged the definition of the dimensionless time, and the temperature at the front wall was found in a similar way. We had to unpack the definition of the dimensionless temperature to get the answer in centigrade. And if you remember that you have to rearrange the definition of the dimensionless temperature to get temperature in centigrade, then all will be well.